Hello, and welcome to the lecture on Chapter 1 of Astronomy Today, 8th edition. In this chapter, we're going to introduce astronomy, and then the title of the chapter is Charting the Heavens, which is just a general title because we're going to introduce a wide variety of introductory topics about astronomy in this chapter and in this lecture. All right, so let's take a look at what we're going to cover. So we're going to cover in 1.1 our place in space, so where is Earth? Then, in the second section, scientific theory and the scientific method. Then we'll talk about something called the obvious way, which is basically just looking at the sky and making sense of what we see. Then the first of two more precise discussions, we will talk about angular measurements. And you'll notice that title, that subsection, that's because every chapter has a few of these basically quantitative sections. These are sections where we get into a little bit of the math behind astronomy. Then we get back into the concepts with 1.4, where we discuss Earth's orbital motion. So that's us orbiting around the sun. Then we'll talk about the motion of the moon, which is the moon orbiting around us. And we'll talk about the measurement of distance. How do we measure distance? And by the way, that's going to be a big reoccurring theme in astronomy, but this is going to be our first time we discuss it. And then finally, in our second quantitative subsection, we will talk about measuring distances with geometry, using something called triangulation and something we'll see more in this class, something called parallax, which is just kind of a special form of triangulation. But more on that in a few moments. Okay, so where is our place in space? Well, Earth is very much average. We don't occupy any special place in the universe. In fact, the universe is all of space, time, matter, and energy. That's a big idea about the universe, and in fact is not the main focus of this course. Here we're going to talk about our solar system, which is very fascinating in its own right, but as far as ideas like the Big Bang and the nature of the age of the universe, that would be a different course in astronomy. But after all, we are part of the universe and this is astronomy, so it makes sense to define it. All right. So why is Earth so average, right? Well, just because it's a rocky, or what is known as a terrestrial planet. It's around a very much common type of star. It has a common type of orbit. That's what we mean by it being such an average planet. And we know this because we've discovered quite a few thousand, in fact, planets around other stars. And we find that many of them are Earth-like. That said, we don't know the details about those other planets. So, to backtrack real fast, to say it's average is a fair statement, but I don't want you to get the wrong impression that we know of other Earths. We know of potential other Earths. We have not been able to, with our limitations of looking at planets around other stars, which is quite a feat and something we'll touch on briefly in this class. We don't know about their atmospheres. We don't know if they support life, certainly. So we don't, in fact, know if there's other Earths. But the very basics of Earth are average, which means that there probably are other life-supporting planets like Earth. We just haven't confirmed it. All right, so moving on. Astronomy is, as I said a moment ago, the study of the universe, okay? That's a huge topic. And again, in this class, we're going to focus on studying our sun, Earth's orbit, the other planets in our solar system, and the moons around those other planets, and asteroids and comets, okay? Scales, oh my gosh, scales. They are very large, very, very large. The scales between stars are measured in light years, okay? That's how far light travels in a year. So a light year is a distance, like a mile, or in the metric system, a kilometer. A light year is about 10 trillion miles, which actually is kind of rough rounding. It's really about 6 times 10 to the 12 miles. That would be 6 trillion miles, because 10 to the 12 is 12 zeros. That's a trillion, which is 1,000 billion, a billion being 1,000 millions, right? So actually, if we really want to think about 10 as our rounding number, you can say it's about 9 trillion kilometers, because a kilometer is shorter than a mile, okay? All right, so there we have the idea about how big a light year is. A trillion, that's unimaginably large. The distances in the solar system we'll see are more in the matter of light minutes, okay? A light hour, the real limit of like the size of the solar system. So the distances are going to be quite a bit smaller, and we'll actually talk about other units that we'll use for measuring those distances. Obviously, we'll just use hundreds of millions of kilometers, but we can also talk about things called astronomical units. But we'll talk about that in a later chapter, okay? But for now, an important scale is the light year, okay? So our galaxy, again, because we're talking about the place of Earth in the universe, our galaxy is 100,000 light years across. Whoa, think about that, right? Because one light year is almost 10 trillion kilometers. So if you have 100,000 of those, that means that's 100,000 times 10, or a million, because 100,000 times 10 is a million trillion. The galaxy across is a million trillion, okay? That would be 10 to the 17, okay? 10 to the 17 kilometers. That's 17 zeros. Also, just the fact that light, the fastest thing in the universe, something that travels so quickly that it can circle the Earth many times over in just a fraction of a second, something that travels that fast, it takes it 100,000 years to stretch across the galaxy. And the galaxy is just one of many. Okay, so those scales are unimaginably large. And again, let me stress the fact that even though we're going to be focusing on our one little small solar system, which is one little pixel in this picture, right? Smaller than a pixel, in fact, that that solar system is still vast. It takes spaceships, space probes, manned missions, many, many days to travel between planets. Okay, I mean, just to get to the moon takes a many hours. To get to Mars, when we send the robotic missions to Mars, those take months because that's how far the distances are. And they're not going at sluggish speeds; they're going at speeds of tens of kilometers per second. Okay. So we're going to take a little diversion here and talk about science itself and the idea of scientific thinking and the scientific method, okay? Which is this idea that there should be a process of testability, accountability of your ideas. If you want to have ideas that allow you to do things like engineering feats, like understanding the world around you, because you can't just guess at it. You have to make sure that you're right or you're willing to find out where you're wrong, okay? And able to find out where you're wrong in your theories, okay? So scientific theories must be testable. They must be continually tested because some new information can show that the theory was incomplete, okay? They should be simple as possible. You don't have to have over complexities because most likely that's wrong, all right? Your theory should be as simple as possible, which is to say, in other words, they should be elegant, okay? Scientific theories can be proven wrong. They often are, okay? But they can never be proven right with 100% certainty, okay? Because they're always being continually tested. If you're right with 100% certainty, then you are overly certain. All right? So the method involves observation, theories, and predictions. Okay? So an observation leads to a theory explaining it. So we start with observations, what is sometimes known as curiosity-based research. Just observe the world around you, observe the sky. Okay? Then, based on those observations, we find a model, which is our theory. Then we say, what does our theory tell us? How can we actually test our theory? We need to have testable predictions because only then can we see if our theory holds up, if it actually is correct. Because if it doesn't pass the test, then we go back to the drawing board and we get a new theory. Okay? All right. So that's a little side note about what we're talking about here because, of course, astronomy is a science. Okay? All right, so let's look at the night sky. That's a great way to think about astronomy. The first thing that comes to mind when many people think of what is astronomy, what do astronomers do? Well, they look through telescopes, they look at the sky. That's absolutely true, okay? Sometimes they don't look at visible telescopes, sometimes they use radio waves or other types of electromagnetic radiation, but more on that later. But again, if we're doing curiosity-based observations, then we're going to look at the night sky, which is fascinating and beautiful and makes us wonder about our place in the universe. Okay? So there are about 3,000 stars that are visible to the naked eye. Okay? They're randomly distributed, but we like to make patterns. That's often attributed to the human brain, that it likes to find patterns, and often those patterns then allow us to understand the world around us better. And for thousands of years of humanity, people across the world have been making patterns with the stars in the sky. And the obvious way of doing that is to make constellation, figures that have some meaning. They tell a story. Okay? Some constellations are useful, like Polaris, which is due north. Why would that be useful? Well, think about navigating in the ocean. You then know directly the direction of north. That can get you somewhere, find your way home. Imagine being lost in a storm, seeing Polaris when the sky clears, and knowing that that's the way you can start heading until you hit land, right? Okay. But constellations can also be useless, which can have no practical purpose. And a great example of that is astrology. Astrology is just a system of beliefs or myths or legends that don't tell us anything. They might be fun, but they have no practical use. Okay? Now, an interesting thing about looking at the stars in the sky, and a great way to start expanding our idea, because astronomy is very much about expanding your idea and being able to visualize the Earth in the vastness of space, orbiting, moving, the stars surrounding us in 3 dimensions, right? Well, when you do that, you have to realize that stars that might be all close together in the sky, the night sky, your local sky, as we often say, that those stars aren't close together in space itself, right? Example here, you're looking at a bunch of stars that appear in a little cluster in your local sky, but some of those might be close, some of those might be very far away, because the idea is it's a 3 dimensional picture. And some of these stars are as far as maybe nearly 80,000 or excuse me, 800 light years away. Okay, and there are a lot of stars within a radius of 1,000 light years from Earth. Okay, this would be a fairly accurate idea of this distribution of stars. They're distributed in a 3D way. Okay, and so that means that the distance between, say, this alpha star, that's the Greek letter alpha, and this gamma star over here, or actually it's delta, excuse me, that star, the distance between them is vast. They're nowhere close to each other. They're a huge distance. It would take light many years to travel from one star to another. They just appear close from our observation vantage point on Earth. Okay? All right. So, continuing then with that idea and that the stars that appear close in the sky aren't really close in space, well, then that means that maybe the location of the stars in the sky is useless, right? It's just they're there, right? But it's a great starting point because it does allow us to say, okay, well, you can quickly go and know where to look for them. We know that that star in the sky is next to another star. So then if you need to move your telescope from one to another, that's useful information, okay? It is good to catalog the stars in our local sky, but just be aware that does not mean that they are necessarily close together in space. Now, are there ever times when the stars in the sky are in fact close together in space? Yeah. There are times when there are actual star clusters and the stars are all close together and then they appear close together. But that's definitely the exception, very rare. Okay. But if we continue with this idea then of cataloging the stars in the sky, then we consider something called the celestial sphere. This is an imaginary concept. There's no celestial sphere. We're not surrounded by a sphere. We're just in the vastness of space. Our planet is, right? And everything's in motion. But it's still a helpful imaginary concept. Okay? So stars seem to be on the inner surface of a sphere surrounding the Earth. They aren't, but you can use 2 dimensional spherical coordinates, similar to latitude and longitude, to locate sky objects. See, that's the cataloging of the stars. Okay? That way I can say exactly where a star is in the celestial sphere, just like I could say the latitude and longitude of California is, et cetera, right? Same idea here. Okay? And the equator of the celestial sphere matches up with the equator of Earth because it's like a projection of the Earth's surface onto this imaginary sphere. The poles of Earth, the geometric poles, they match up with the celestial poles. So it's very much like this human construct. Okay? But it's great because it can tell us, where the Dipper is, where Cassiopeia is, where Gemini is, right? And again, not because we care about them to predict our future with astrology or tell us about our love life or something like that, just so we can say, oh, well, there's this star, which is a certain type of star, and it's in that constellation. You get the idea. Okay? Now, when we talk about the celestial sphere, we want to use angular measurements because it's a sphere. Okay, it's not a rectangle or something, or a rectangular solid. It's not a cube. It's a sphere. And if we're using angular measurements, then we want to use degrees. Okay, so a full circle contains 360 degrees. Here's the full circle of the celestial sphere. This little tiny wedge is 1/360th of that full circle, right? And if we continue that edge out, we say that it has 1 arc degree. And if you look at things that are really far away, you can have a relatively large object that only covers 1 arc degree because it's so far away. right? If something was close, it'd have to be small, like a little individual dot, like I just drew, in order for it to only cover 1 arc degree. So you see there's a direct relationship between distance and how many arc degrees an object covers in your vision, in the celestial sphere, right? Okay? That's like, how big is the moon? How big is the sun? Well, the moon is much closer than the sun. Okay? All right? In fact, let me just clarify the idea. When you look at the moon and the sun in the sky, two most obvious things you'll ever see in the sky, they're actually both appear to us as about the same angular size. If we made an angular measurement of the moon and the sun, we get about half a arc degree, half an arc degree, okay, for each of them. That doesn't mean they're the same size in actual space. The sun is so much more massive than the moon. It's just much further away. Okay, it's the difference between 300,000 kilometers to the moon and 150 million kilometers to the sun. Okay, but we can talk about things that are much smaller than, well, an arc degree, because the stars themselves are tiny, right? Or even the distances between stars, they can get really closely packed together. Okay, so we need to be able to split up a degree into smaller pieces, and we do that just like we split up time. We split 1 degree into 60 arc minutes and 1 arc minute into 60 arc seconds. Okay, so then how many arc seconds are there in a degree? Well, think of it. Yeah, I think you got it. 3,600, which is just 60 times 60. Okay, so angular size of an object depends on its actual size and distance from the viewer, as I was talking about, right? That's what I was just talking about the sun and the moon. Okay, all right, so let's now move on to orbital motion, because it's very important to understand that Earth is in motion around the sun. Okay, this is a big turning point in astronomy. We can touch a little bit on the history later in this semester. But now let's just take it for granted, right? We know in the modern world that the Earth is a sphere and it orbits the sun. Okay, well, we have a daily cycle, noon to noon, which is our diurnal motion. Okay, and a simpler maybe term for that, and remembering the word diurnal, is solar day. And by the way, diurnal just means day. An animal that's awake at night is called nocturnal. A animal that's awake during the day is called diurnal. Humans are diurnal. So that's how the adjective gets used. It just means relating to the sun. Okay, but a solar day is diurnal motion. Okay, so great. Now here's the thing: stars aren't quite in the same place 24 hours later. Maybe you've noticed that, right? Imagine you're looking at certain constellations. They're not the same place night after night. Okay? If you haven't, I highly recommend it. Find a really recognizable constellation. It's winter right now, so Orion. Okay? Look at Orion's belt, 3 bright stars. Well, you won't find it in the same place at the same time of night, night after night. It will gradually move until, in fact, in the summer, you won't be able to see it at all. So why is that? Well, that's due to Earth's rotation around the sun. All right? Because when you're in the same place again, okay, so let's read this. When the stars are once again in the same place, a sidereal day has passed. Okay, so notice the example here in the picture. Okay, so we'll start with the solar day. A solar day involves the Earth getting back to its same position relative to the sun. Okay, and this is just choosing some location on Earth where you are. Zoom in on this a bit, right? So you're right here at this point I've circled, and then the Earth's going to turn in a full circle until it's lined up back with the sun. Now, as it's done that, as Earth has turned in its full circle, okay, I'm going to trace this line here, Earth hasn't remained at rest. Not at all. It's been in motion. It's been flying at about 11 kilometers per second around the sun. Okay? It's in very fast motion because it's covering a huge circumference, a huge orbit around the sun. And it has covered about 1 degree in terms of its angular motion around the sun. And that's no coincidence, by the way. That's why there are 360 degrees in a circle, because when the math was first being developed thousands of years ago, scientists, philosophers estimated that there's about 360 days in a year. Now we know it to be more accurately 365.25, but you get the idea, okay? And even that, there's more decimals after 0.25. Okay, so here's the thing though, that's a solar day, getting back to the place where the sun is in the same point in the sky, okay? So rising above the horizon. But notice then that the stars aren't in the same place, okay? The stars have moved a bit. In fact, a sidereal day is always shorter than a solar day because that's where you get back to where the stars in the same place. Okay? So it would be earlier in the evening to find Orion in the same location. Each evening, you have to go earlier and earlier. But if you go too early, then you're not going to see Orion because the sun hasn't set yet. Get the idea? Okay? All right. So that's the difference between solar days and sidereal days. Sidereal days are shorter than solar days. Okay? And this allows for seasonal changes in the night sky. Seasonal changes in the night sky. We have certain constellations that are considered winter constellations and some that are considered, well, summer constellations. Okay? So, right? We have here, southern horizon, and this would be in the northern hemisphere, okay? In both cases here. Let's write that in, northern hemisphere, because there's entirely different constellations with some overlapping in terms of the ones that ride along the horizon between the southern and the northern parts of the Earth. So in Australia, you see totally different constellations for the most part. But look, we have a winter sky, Orion, quite visible, kind of low in the sky, right? Kind of catching your eye. And then in the summer, though, it's totally different constellations, right? Some of the things that become really obvious is Sagittarius, or kind of the long trail of stars that make up Scorpius. Okay, certainly Vega. Okay, all right. This is the basically brightest star in the sky. All right, get the idea. And here it is, looking instead of from the point of view of what you see on the ground, what you could see if you were in some spacecraft looking down on Earth's orbit. In that case, if you took pictures at different points in time, in the months of March, June, September, and December, you'd see that the Earth is facing different directions. Because think about it. When you're in September, you can't see, okay? You can't see stars that are behind the sun, right? Look at the stars that are behind the sun. Virgo, for example, okay? When you're in September, you can't see Virgo because Virgo would rise and set with the sun. And the light of the sun totally washes out stars. You can't see stars behind the sun unless it happens to be an eclipse. More on that in just a moment. That you can't see those stars. So that's why they're not visible in the night sky. Whereas in September, what is visible in the night sky? A constellation like Pisces, like right overhead. Okay? So that's the idea. Different constellations in different times of the year because some are obscured by the sun, right? Okay. All right. So Earth's motion around the sun is an orbit. That's called a planetary orbit. We'll talk a lot about these throughout the semester. But then the apparent motion of the sun through Earth's sky, your local sky, is called the ecliptic. Now, the ecliptic is a term that would be thought of best as being associated with the celestial sphere. It's a track or a path along that celestial sphere. So just like the celestial sphere, it is an imaginary idea, okay? So the ecliptic is a plane of Earth's path around the sun. It is at 23.5 degrees to the celestial equator, right? The celestial equator, again, being that projection of Earth's equator onto the celestial sphere, okay? The northernmost point of a path about the celestial equator is the summer solstice, okay? The southernmost is the winter solstice, okay? Points where the path crosses the celestial equator are called the vernal and autumnal equinoxes. Excuse me. That's the time where the sun has equal time of day as the moon, okay? Or, as night. There's 12 hours of sunlight, 12 hours of darkness on the equinoxes. They're equal, all right? The solstices are when the day is either longest or shortest, depending on if you're in the northern or southern hemisphere, okay? Because the winter solstice for us, what we call the winter solstice, which is a northern hemisphere term, that's our shortest day of the year, okay, around Christmas. Well, that same day, say December 22nd, which is either the 21st or the 22nd, that's a winter solstice. That same day in the southern hemisphere is the longest day of the year, okay? And that's because of Earth's tilt, okay, that 23.5 degree tilt. Because the fact that the ecliptic is tilted relative to the celestial equator by 23.5 degrees is because the Earth is tilted at 23.5 degrees to the ecliptic, really to the plane of the solar system, okay? All right, and the seasons, the reason it's colder in the winter and warmer in the summer is because of the sunlight angle and the length of the day, okay? That means you get less heating from the sun, okay? And the whole deal about the angle is because it's the same amount of energy, and if it's spread out over a small amount of area, then that energy is then able to heat up the ground, heat up the water, heat up the atmosphere. If that same amount of energy is spread over a long area, because you're tilted or you're just very near one of the poles, then that means less ability for that energy to heat up the gas in the ground and the water and so on. Okay, but the time of the day is important too because it's just less exposure to that radiant energy of sunlight. Okay, so Earth has that tilt, 23.5 degrees. It actually never changes, but it does precess, just like a spinning top. Okay, just like a spinning top has a particular angle, and if the top was completely frictionless, it would never stop spinning; it would just keep spinning forever. And then that top then would always precess at that same angle. That's what Earth does. Okay. Now you might be like, well, is it entirely frictionless? Is Earth gradually? There are some effects of other gravitational pulls from Jupiter and some tidal forces with our own moon that are affecting things very slowly over billions of years. But over tens of thousands of years, there's no difference in Earth's tilt. But what there is there's a precession that interestingly takes 26,000 years, which is pretty fast for astronomical phenomenon. You know, if you were to look at Earth's entire lifespan of 4.5 billion years, it would have precessed many times, right? If you sped up those 4.5 billion years, 26,000 is a tiny fraction of a billion. Because remember, there's 1,000 thousands in a million, and then there's 1,000 millions in a billion, right? So we're talking tens of thousands of precessions that have occurred since Earth was formed. Okay, but in human time, 26,000 years is a big time, right? The humans hadn't even built their first cities 26,000 years ago. They were still living in caves and doing cave paintings. Okay, but in that time, Earth completes one complete precession. So it goes like this, which means different stars appear in the sky. It totally changes the constellations that are associated with particular locations. For example, the best way to think about this, the simplest way, is Polaris, because currently Polaris aligns with our geometric North Pole. I say geometric because it's not our magnetic North Pole, okay? But it aligns with our geometric North Pole, the actual axis of our rotation. So we look, and that's due north, right? That's taking it to the North Pole. Now, it won't, however, line up in 14,000 years, okay? In 14,000 years, Vega will be the North Star, right? Pretty cool, okay? So it really changes dramatically. And also, if you think about astronomy, at least in kind of the Western tradition, was into the constellations that we know that came from the Greeks, that was all being initially written about 3,000 years ago. Well, 3,000 years is an appreciable fraction of 26,000. Okay, so there's been significant changes, and in fact, if you look at the recordings of Greeks, they find out that there's big discrepancies because the stars have moved substantially since then. Okay, all right. So more about Earth's orbital motion. The time for Earth to orbit once around the sun relative to fixed stars is called a sidereal year, okay? Whereas a tropical year follows the seasons. The sidereal year follows constellations. In 13,000 years, July and August will still be summer, but Orion will be a summer constellation, okay? All right, so it's a difference between returning to where the stars are versus returning to where the sun is, okay? All right, so now enough about Earth's motion. Let's talk about the motion, which affects our ocean, but the motion of the moon, our one natural satellite, okay? All right, so the moon takes about 29.5 days to go through a whole cycle of phases. We call this the synodic month, okay? Now, again, no coincidence, that's about equal to a calendar month because that's where months come from, of course, okay? All right, now, synodic month, one complete set of phases, okay? All right, well, what are the phases? Well, the phases are due to the different amounts of sunlight, well, the sunlit portion, being visible from Earth. Now, let's take a look at this picture. I'll zoom in a bit on it, okay? So imagine you're here, right? North America. And over a given day, you're gonna spin, the Earth's gonna spin in a full rotation in 24 hours. Okay, so this arrow here takes 24 hours to complete a full circle. Okay, so in that time, you come back and the moon has moved a bit because the moon is going this way and it's orbiting around us. Okay, it's orbiting around us in a way where it's taking a certain amount of time to complete that orbit. Okay, which we will mention in a second, which is called the sidereal month. Okay, so it's physically moving around Earth. Does that make sense? Okay, the moon is physically moving around Earth. Okay, based on the mechanics of its size and its distance and so on. okay? So that's the moon spinning around Earth, orbiting around Earth, okay? Now, in that, as that happens, each day the moon will have moved a little bit, right? Not too much, right? It's, so that every subsequent night, you notice a gradual change with the moon, because by the time you've gotten back around in 24 hours, how far has the moon moved? Well, it's only moved about a 30th. Let's be rough here. It's moved about a 30th of its full orbit, okay? So a little bit of change. But it starts to really matter after a few days. Because if you start at the point where there's a new moon, okay, a new moon being a moon that's completely dark, after a quarter of the moon's orbit, which is about how long? Well, it's about half of 15, so let's say 7 days, okay? So after about 7 days, you look up and the moon's not totally dark anymore. Now you have what's called a first quarter moon. The moon would look like this, okay? All right, well then you wait about another 7 days and you go out to it's clear night and you go out and you look up in the sky and now you see that it's a full moon. It's the opposite of a new moon. It's totally bright, okay? And then another 7 days, and you go back to what's called the third quarter, okay? Which looks like the first quarter, but on the other side. And then the process, will repeat over and over again, okay? And why is that? That's just because of the relative position of Earth, the moon, and the sun, and the resulting sunlight from the sun, okay? And the sun is so far away that light is coming in completely parallel like this. And if the moon is between us and the sun, then the moon is dark. Also, the time that the moon rises and sets will vary. New moons rise with the sun and set with the sun, because the rising and setting is just apparent motion due to, you guessed it, the 24-hour Earth rotational motion around its own axis. Okay? Now, the full moon, when will it rise and set? The full moon will rise at sunset and will set at sunrise, because in that case, they're completely sharing the sky. They're never around at the same time, okay? In fact, the full moon is the only time that the sun and the moon aren't jockeying for sky position simultaneously, okay? Does that make sense? Because the quarter moons will always the quarter moon will always be up during daytime, at least either in the morning or the evening, okay? All right. So those are the phases of the moon. Now, the phases, that full month, the synodic month, that's from the Earth's perspective. But if we were to zoom out and just watch the moon's orbit, then we'd get a sidereal month. Because the sidereal month is just the time it takes the moon to go all the way around. But remember, just like the stars, if the moon goes all the way around, it's not quite back to where it started relative to sunlight, because Earth has moved a little bit in its orbit around the sun. And since Earth has moved a little bit in that time, then the moon has to go extra far to get back to finish its phases, which is why the sidereal month is shorter than the synodic month, just like the sidereal day is shorter than the solar day. So you can remember sidereal is always shorter. Okay. All right. So more about the moon, okay? We want to think about the moon shadow and Earth shadow, because we're talking about something that's very fascinating, eclipses, okay? So let's just first start here and think about a condition that is unfavorable and favorable for eclipses. So an eclipse is when the moon completely lines up with the sun, or the moon completely lines up with Earth's shadow. And there's the two types of eclipses, and I'll be very clear which is which, okay? But to do that, we have to have alignment along a certain line that matches up with sunlight, the light from the sun, okay? And it turns out that the moon isn't always on that line. So there are times when we have unfavorable conditions for eclipses, okay? And we'll talk about why that is and when that is in just a moment. But if everything's lined up, sunlight and the moon and Earth are all perfectly lined up, then we have favorable conditions, okay? All right, so that's a great place to start. And notice that the maximum angle of unfavorable conditions is 5.2 degrees, okay? Why is that? Well, hold on to the thought, okay? All right, so a lunar eclipse, this is one of the two types of eclipses, is when the moon is in Earth's shadow, okay? So that means that the Earth is between the moon and the sun, see? Because the sun is over here, right? Big giant sun, right? The Earth is between the moon and the sun, okay? We have a partial lunar eclipse when only part of the moon is in the shadow, okay? So maybe the moon just kind of, kisses the shadow of Earth, kind of passes into a little bit, then it passes right back out of it. That creates a partial lunar eclipse. But if the moon is completely in the shadow, then it's not getting any direct sunlight from the sun. And that creates what's called the red moon, because then all the light that is reaching the moon is the refracted, which means bent, light of all the sunsets around Earth's perimeter, which then, of course, gives that red color because of the particular wavelength that is able to survive through the large amount of atmosphere following the refraction of light. Okay, there's a lot of kind of physics built into that, but that's what happens, and that's why the Earth or the moon appears red during total lunar eclipses. Okay, when the Earth is between the sun and the moon. Okay, now the other type of eclipse, and definitely the more dramatic, interesting type, is the solar eclipse. And the solar eclipse occurs when the moon is between the sun and the Earth. Okay, now the Earth is the far one out. Okay, now we can get partial solar eclipses when only part of the sun is blocked by the moon. We can get a total, okay, that's like this one here, a total when the moon exactly blocks the sun. And we can get an annular solar eclipse when the moon is slightly too far away and its angular size isn't quite big enough. Because it's a remarkable coincidence that the angular size of the moon and the sun are about the same. But it's not always the case. The moon has what's known as a elliptical orbit, which means it's not always exactly the same distance from Earth. All orbits are elliptical. None of them are perfectly circular. Okay, we'll talk about this when we talk about Kepler's laws in a later chapter. But the point is that because of that elliptical nature, sometimes the moon is slightly further away. And if that coincides with the right conditions for a solar eclipse, then the moon just might be relatively too small in terms of its angular size and not completely block the sun. Now that's pretty rare, right? Usually the moon is plenty big. There's a lot of kind of leeway in that case. But interesting fact, over time, in a billion years or so, the moon will be so far away that all solar eclipses will be annular. And that's because the moon is gradually receding from Earth, which is quite fascinating. It's due to the tides and the loss of energy because of that tidal friction. Okay? But these are the types of solar eclipses: partial, total, and annular. Okay? When the moon is blocking the sun because the moon is between the sun and Earth. Okay? Now, why don't we have eclipses every month? Because if we look at these pictures, and let's go back, if we look at these pictures, the conditions for solar eclipses are new moons because the moon has to be between Earth and the sun. That's a new moon, okay? If we look at the condition for a lunar eclipse, that's a full moon because the moon has to be on the other side of Earth, okay? So really, it's full moons and new moons. But why isn't it every full moon and new moon that leads to eclipse? That's because of those favorable and unfavorable conditions. Because the rotational plane, the orbital plane of the moon is tilted at 5 degrees, just about, right? 5.2 degrees. It's actually tilted relative to the orbital plane of Earth. And that tilt means that there's only certain times of the year that are favorable for eclipses, eclipse seasons. Okay? And that's our location in space as Earth orbits the sun. Right? So quite interesting phenomenon. If the orbital plane of the moon was lined up with the ecliptic, which is to say the orbital plane of Earth around the sun, then just about, if it was perfectly lined up, then actually every single new moon and full moon would be an eclipse. Imagine that. That'd be kind of cool. That's just not the way things worked out. Okay, during the particular conditions of how the moon was formed so many billion years ago. Okay. All right, so enough about the motion of the moon. Let's do one of our last sections here and talk about the measurement of distance, okay? Measurement of distance. How do we do that? Well, the thing, and this is just one of the biggest ideas in astronomy, we don't go out and measure things. Certainly when we talk about stars, we don't go out and measure them. There's no way. We can't travel to stars. They're too far away. I mean, we can barely even travel to things in our own solar system. Just in the last decade, we managed to get probes all the way out to Jupiter, all right? Well, excuse me, I meant to say Pluto, right? But even good high quality photos of Jupiter in the last decade, okay? But recently we had a probe that went all the way out to Pluto and finally got close-up photos, right? But that took decades to even get there. I mean, we had to design the thing, but then we also, it took over 10 years for the physical probe to travel that far. Imagine that, okay? So that means a lot of times we can't actually just directly measure the distance. We have to measure it using geometry, okay? Now, triangulation is the term for that. You measure a baseline, that'd be on Earth, or maybe Earth's orbit, and then you measure angles and then calculate the distance, right? Using right triangle geometry in this case. Now, something called parallax is basically creating a isosceles triangle that we can then split into two right triangles. So it's basically triangulation, but we're doing it with Earth's orbit as our 2 points, and then measuring the motion of stars with that parallax concept, okay? So another way that angles and measurements can be brought together was done about 2,300 years ago, right? There's one of those Greek philosophers, this fellow by the name of Eratosthenes. And it's such a great example of it because the idea was that the angle of a shadow at two different locations was used to measure Earth's circumference. And yes, the Greeks in the Ptolemaic era, they did think that Earth was a sphere. It was later on that the kind of idea of Earth being a sphere got rejected for a few hundred years, right, during the Dark Ages. But point being that Earth was thought to be a sphere, and thus this experiment was proposed as a way of kind of showing that, yes, it was a sphere and getting a good estimate of how big that sphere was. And remarkably, Eratosthenes was able to get pretty close to the actual size of Earth based on more modern techniques. And it was all with angles of shadows, okay? So he did it by notice that the sun was directly overhead in one city and was an angle in another. And by measuring the angle of the sunlight in the one city and the lack of angle in the other city, basically having sunlight go down in the well. It's a good way to get exactly, that's a really good way of finding that sunlight is directly overhead. If you have a deep well, because you can look down and you can see the reflection of the water, and you know the sun is directly overhead. And then he knew the physical distance between the two cities, Alexandria and Syene. He knew they were 300 kilometers apart or something like that, right? Pretty accurately, just by kind of like tracing out the steps, okay? And it was a common trade route, so it was very well documented. And so there we had that distance between the two cities. You had an angle, and he rightly supposed that this portion must be a portion of the overall, that distance between the cities must be a portion of the overall circumference of Earth. And thus the ratio of the 7.2 degrees to 360 degrees, that ratio must be equal to the distance between the cities, which we'll call delta x here, over the entire circumference of Earth. And the circumference formula is 2 pi r, where excuse me for that, where r is the radius of Earth, okay? There you had it, calculation of radius of Earth. Remarkable, okay? All using angles and one measurement, the one measurement being just the distance between Alexandria and Syene, okay? Okay, and we can measure distances with geometry like a planet going around in orbit, okay? 2 pi r, again being that same idea that I just showed before, okay? And here we have the angular diameter of an object and a known distance, and that allows us then to calculate the unknown diameter. So this is really helpful for, say, finding the size of asteroids or moons. We know their distance based on other measurements, but then we just need to measure their angular size, and then we find their actual size. Got it? Okay, because if something's further away, it will appear smaller, right? We're familiar with that idea, okay? And that's angular measurements using geometry. Okay, so the summary of this chapter, hopefully this has been a very interesting lecture, but let's wrap it up and summarize it. We have astronomy, study of the universe. Scientific method is a process of observation, theory, prediction, back to observation, okay? And testing, okay? Stars can be imagined to be on the inside of a celestial sphere, useful for describing locations because you have latitude and longitude on that celestial sphere. The plane of Earth's orbit around the sun is called the ecliptic. It is 23.5 degrees to the celestial equator because Earth has a tilt angle of 23.5 degrees, okay? That precesses over a 26,000 year period, okay? We'll have that in 26,000 year precession, okay? Then we talked about the angle of Earth's axis, in addition to precessing over 76,000 years, causing the seasons within a given year. Okay. Then we talked about how the moon shines by reflected light and has phases. Okay, because the light we see from the moon is just a reflected light of the sunlight. Just to be clear on that, and the moon doesn't create its own light, right? That's always reflected sunlight. That's why we see phases. Okay. We talked about the difference between the solar day and the sidereal day. We talked about the difference between the synodic month and the sidereal month. And which one's always shorter? The sidereal. Okay. We talked about the difference between the tropical year and the sidereal year due to the precession of Earth's axes. We talked about the eclipses of the sun and the moon, okay, when they occur, why they don't occur at every full and new moon. and we talked about how distances can be measured through triangulation and parallax. Okay, well, thank you so much for watching this lecture video.